Hello, everyone. We are Saturday, February 1st. That's crazy. We're already February. And today we're going to be continuing. Mm, Yesterday, did I do work? No, I didn't do any work yesterday, but 2 days before, I was reviewing. We sped up matrix multiplication by 10x, and I finally, I guess, like really understood how memory works and the stack pointers and um, like what the purpose of the stack and the heap and how your memory is divided into different sections. Um, so you have your stack, which grows downwards from high memory addresses to lower memory addresses, and you have your heap that grows upwards from lower to higher memory addresses, and then you have a section for your global data or static, and then you'll have a section for your code, right? And so when you have function calls nested in function calls, during that process, you want to store like save the current context. So you use the stack to store all of those local variables, and then the global variables will be stored somewhere else in memory because that should be accessible throughout the entire program. Um, I guess there's a few follow-up questions. One is, if you have multiple files that are being run, does that have anything to do? Like, you know how in static variables that restricts the visibility of a function of a variable to that translation unit. So if you have multiple static variables with the same like variable name, I guess like in memory, it would they would know it. All right, so let's ask. I'm not sure about that. How there is a section of memory is dedicated global if there are two static variables, the same variable name that are used. What is going from memory perspective? But how does the compiler search program know which static variable it needs to access? And you know how you have classes in private and public methods. Like how does visibility work? How is the visibility of a variable restricted? Like classes public versus is just a compiler thing, or how it from hardware perspective. Yeah, it's still it's plain data. You can access the private data. There's no runtime protection, right? It's just like at a compiler level, it's done. Like hardware doesn't enforce this. If you want to enforce things at a hardware level, you'd have like kernel mode versus user mode. Memory protection units. What about static variables? That is only enforced in hardware. I see. Okay. Uh, Is it computer memory where I wrote? That's not where I wrote. See, memory model. Yeah, memory model. Computer memory. So one other thing I was confused about is, okay, so we understand how it works at a process level. So that's sort of like what I learned in my CS241E class. But then at the operating system level, there are also stacks that are being used. And what we're gonna look at it is, I guess, like in this context switch, yeah. So inside your process, you have your program counter, that's just a register, and then you have general registers, and then the stack pointer is also a register pointing to somewhere in the stack. But you see the control stack here is not referring to the stack of your program. It's a general stack for doing control. So let's review how this works, because I forgot. So when you search a context, you save the context of the processor as, okay. Yeah, so you store this in the process control log. And where is the PCB stored? Process table. Yeah, so you have a process table that stores metadata about the process, right? Because when you context switch between different processes, you can kind of think of it like when you make a function call, you need to store the current context, so that when you return to that process, you know what the state of your register is. You can like go back to the whatever state in whatever program you are running, and so that information will be stored on the PCB. So right before you enter a process, you'll look at the PCB and then load load the values into the correct registers, and then you'll be able to resume your program. And then what's the control stack for then? The context of the process before calling an interrupt service routine. I see. I guess very similar to a program stack. I use a stack, right? Like when you have nested function calls, you could also have nested interrupt service routines. So each process has its own dedicated control stack. I see. conversation not loud. I'm confused. I mean, a stack frame just means like elements of the stack. So yes, there's another kernel stack, and I still don't fully understand what the kernel stack does. So there's a kernel mode stack. Okay, I was thinking about something. For this heap memory can grow upwards, right? I also learned this in my OS class. First fit. this. Hmm. I remember those. Yeah, right. It's kind of strange. You're in trance. That means that you can re-enter and expect the state to be restored. All right, lock in. No, that's a conversation, bro. I don't think this is correct. You don't. What? So a control stack is very similar to a kernel stack is very similar to a user stack. The difference is that a user stack is just generally used at the program level. So let's say you write some function, you call a function within a function. So you'll store the current or your stack stores like the values, the variables, and it will store the program counter to like that. So imagine you have foo, and then you allocate some variables, and then you call bar. Before you jump to bar, you will store the program counter. Actually, it's probably you'll store the current values. Is that how it works? Or is that? Yeah, I think so. are the values of the variables before a function jump are the values of the local variables at the last minute, or it's just pushing a new stack frame. The stack will store the current context, and then it'll push. And if the function takes arguments, those will also be pushed onto the stack, because why can't they pass? Be afraid they might get overwritten. I guess the arguments, it depends on implementation, but like in modern implementations, you simply just push, the arguments are passed by registers, but you do need to push like the program counter, the return address for. So when foo calls bar and then bar is finished calling, it needs to know the return address. So that return address is pushed. So you push the return address. Let's say right before is the return address pushed first, or are the local pushed? See, in my class stack frame, there can be I guess variables don't exist. Like variables is a higher level programming concept, right? Like when you look at the hardware, you don't know what variables are. You either have things in memory or you have them in registers. So when you context switch, or sorry, when you make a function call, right? Um, at a hardware level, like like say A and B, you have A loaded into that register, and then B loaded into another register, and then you make some function call, and then you use A plus B, right? You call A plus B, but it's a local variable, like it's not supposed to be modified. Um, like instead of writing it to memory, right? You load it, but A and B, like like for A B, do those actually is in the stack? So when are local variables stored in the stack? I guess when you have don't know what a closure is, but this comment was pretty helpful. Yeah, so you can optimize the variables, but so the main thing that gets pushed is the return address. It needs to be updated for the program counter. Such arrows. Be careful. Okay. Oh god. If it's unoptimized, it will all the local variables will be stored on the stack, right? And so before you context switch, like I'm a little confused because I guess like you store the state of the local variables, you store their values, and so if like you could have all your variables to exist in a stack, and whenever you use them, you load them onto registers, uh, and then you do the computation. And so it doesn't matter what the values of the registers are, because afterwards, when you compute, you use any of the variables, you will load them into your registers. But that's a really slow, right? Because you stack, okay, there's caching, but you're still reading from memory, right? Whether it's cache memory or like main memory, it's still reading. Whereas if it's directly already in your registers, it makes your life a lot easier. So that's why generally, if they are already in registers, we can just like keep them in those registers, and we can just keep track of things at a register level. But if you keep track of things at a register level, and then yeah, you have like, imagine you compile code or like your assembly code, right? Like that just has assembly instructions. And if you assembly instructions work by looking at registers and memory, and you might have incorrect, like you use x6 register 6, and then use that, like assume, like the program assumes, oh, in register 6, that's variable A, right? And afterwards it adds at register 6 to register 7. But then if register 6 changes after the function call, then that's really bad, right? And so the idea is that you want to like generally after a function call restore the state of those registers. Do you always are the state is the state of all registers restored to the previous call stack frame, or just the ones that are needed? How the compiler which registers? Callie save. Callers. Yeah, caller save. Is that the same link or not? Probably should say link. Foo calls. I don't fully understand this. So some registers are call save and some registers are call save. The difference is that call save means that there are no guarantees that after the function call, those registers are the same. So they're saved by the caller should restore them after the function call. Whereas call save has this guarantee that after you call them, it should the function that being called should restore the state of those variables. So the stack pointer should restore the value of stack pointer afterwards. Oh, holy fuck him. You should restore it. Yeah, okay. That makes a lot of sense, boys. Alright. Alright. I guess finally went down the rabbit hole. Okay. Do I understand everything now? There's always more to learn, but I think it was a good refresher. I really need to get back into deep learning, but I think understanding this at a level is still very, very important. You know, although all of this knowledge the AI already knows, so I don't know if like what I'm learning is actually useful. But I mean, it's fundamentals, right? Like you should know your fundamentals. Or is this too technical? I don't know. You know, I still like don't fully understand how transformers work. So probably, I've seen this paper has been, the diagram in this paper has been shown like a million times. Positional encoding. There's a softmax over your probabilities of words. Yeah, I know. The atom optimizer. How does a gradient update work? Oh, damn! I might need to take a break here. Yeah, I might take a break and then get back into actually looking at transformers or deep learning. Alright, I'll see you guys later.